Hey, good day, everyone. I hope you are all feeling energetic after a big lunch. So basically, I think you already got enough today morning from Broadcom and Meta about Ethernet fabrics for AI. So this is an introductory level talk. So we are going to just walk through some of the basics on the AI fabrics and how Sonic can support that today. Let's move on to the next one. Right, before I dive into AI fabrics, I just wanted to give a picture of what is AI fabric, what fabric we are talking about. Right, there is always confusion. Even today, Ram was mentioning in the keynote today, right? When we talk about, oh, this is a front-end fabric, this is a back-end fabric, right? So as you know, everyone knows there are different kinds of fabric available today. The management fabric for your management connectivity, the cluster or access fabric for the user access, and the storage front-end fabric for the storage access, and then there's a backend fabric as well for the storage, which is not shown in the diagram. Those are all converged. So what in particular we are going to talk about today is about the GPU fabric. When we talk about the GPU fabric, there are two set of fabrics we are talking about. There is the intra-GPU fabric, which is internal to the node, which is currently its proprietary NVLink or XGMI or Ethernet in case of NVIDIA, AMD, and Intel, right? And then there's an external GPU fabric, which is the inter-GPU fabric, which helps you communicate between the nodes, right? That is the fabric we are going. When people refer to AI fabric, I want to make sure that it's clear what we are talking about. All other fabrics are Ethernet today already. We are saying that Ethernet can solve this as well, and Sonic can enable that. So that's what we are going to show you today. And in that particular inter-GPU fabric, again, there are a couple of options. There's a direct GPU fabric and indirect. What I mean by that is GPUs directly expose a NIC out of it, like Intel Gaudi, where directly connecting. You can connect to an Ethernet fabric, or it comes via the host NIC interface, where via the PCIe interface, it comes via the host NIC and then connects to the GPU. So that's what we are going to talk about. Most of the networks today are coming via the host interface, the PCIe, but there is a bandwidth limitation there. If you look at the internal GPU fabrics, they are close to 1 terabyte going further beyond. We are not there yet, so that is blocking. So eventually, next iteration, you'll see those GPU interfaces directly exposing those NICs outside for you to connectivity, right? Next slide. Yeah. So when we talk about Gen AI, right, so I'm specifically changed my heading from AI to Gen AI because Gen AI is what puts stress on the network. When we talk about, there are three types of workloads we are talking about. One is the training, which is the heaviest and compute-intensive stuff, right? It's an offline kind of work environment, right? And then the fine-tuning part of it, which is a smaller scale version of training. It has a different set of requirements. And then finally, there's inferencing where you people go and deploy. This is a user-facing online requirement, right? For all those Gen AI fabrics, the GPU fabric is also there, and storage fabric, all the other fabrics you saw, everything is there. But our focus today is just purely on the GPU fabric, right? You would have seen a really nice slide from Meta today in the keynote about all the different parameters for this type of workloads and all the different things going on to make this as challenging for network fabric, right? So I just want to, so when you talk about Gen AI fabric, there is a large, it's a compute intensive and data intensive, so there's a large volume of data exchanged. And if you say it exhibits a diverse set of patterns, traffic patterns today. If you look, let's go one by one, right? So the workload type. So as I said, training and inferencing, everything has a different kind of problem. Training is network data heavy, so you have this network bandwidth is so much. In the inferencing case, it's latency heavy. And then if you come down to the next one, the model parameters, depends on how you tune your model parameters, how many layers, and how many batch. So the batch size determines how long your traffic is going to be big, right? If you have a longer batch size, it's going to take longer compute size. If you have smaller batch size, you're going to have short packets coming out, right? So those are going to change your thing. And the next, the communication algorithms. So each of the communication algorithms are different, they all reduce. If you take, so the difference, so if you have mesh network, Meta talked about DLRM use case where there is kind of a mesh network where you see a lot of heavy traffic and a lot of congestion. If you're taking LLM, it's all elephant flows and huge sustained traffic where traffic saturation in the network becomes a challenge because of the low entropy. So the next ones are the topology and the communication libraries today, Nickel, Rickel, all those things today, right? They optimize based on the topology discovery of the GPU. So if you are running a rail topology, so they will try to use the enter a GPU node first, and then before getting out to the exit, right? So all those algorithms, the parameters you're choosing for those libraries is going to change how the traffic pattern it is. And then the optimizations, on top of all those things, there are different optimization because today you cannot fit a model in a single GPU. You have to split the model into multiple GPU, that is a model of parallelization, and you cannot fit all the data into one single GPU, so now you have to split the data into multiple small batches, right? So all those optimizations brings in a different set of traffic patterns to each of the workloads. And finally, the model type itself, as I said, DLRM is a mesh network, and LLM is a heavy traffic, so there are a mix of traffics, depends on which model you are trying to choose. So the traffics as peaks and valleys, based on, because when the operation is happening, there is a period of time where compute is busy and there is a period of time network is busy. So it's a quasi-periodic with peaks and valleys, and highly ordered in case of training, predictable in case of training, but inferencing, it's user load, it's highly unpredictable, and how it comes based on the user demand. And as I said, right, the traffic flow is also heterogeneous. It's either large flows for communication for when you exchange your gradients and parameters, or small flows when you exchange your control information using gRPC kind of things. Let's move to the next. I had to rush fast, I guess. I'm already. So before going into further, I just wanted to give you a deep, because in order to design your better network infrastructure, we need to understand the workload itself a little better. So this is key to understand, it is imperative to understand this to optimize your network better. I just wanted to leave a quick sneak peek. I'm not going to dive into much details. I'm trying to simplify it, much of the things, right? When you talk about AI training, most of the things are done in neural networks today. So your data is in the batches divided into sense to all these neurons where they have weights. And then based on it, they're going to compute your answers, output. You're going to see whether the output is right or not. And then you're going to back propagate your weights. So they'll fine tune the weights accordingly so that you get your model accuracy. Until that happens, this loops continues to happen. Okay, at the backward progression where the magic happens, right? So first step is your model is getting distributed to all the GPUs, right? That's a storage access. And then you go into this AI cycle where you read a small set of batch of data, run through the neural networks, and then come back with updated ways. You'll go through the cycle. And then finally, once in every few hours, you'll try to checkpoint your model. Whatever you have gained, you don't want to lose it, so you'll checkpoint back the model into storage, right? You will have a storage access there. So this is your typical flow in the AI training, anatomy of AI training, right? And then again, we talked about different patterns. I just want to give a quick sneak peek of how does the data parallelism optimization changes the traffic flows. If you look at the data parallelism, it's trying to split the data into multiple batches, and then training is performed all the GPUs. I'm showing only one GPU there in the top when you see, so there are multiple GPUs. If you look at it without any optimization, if you do that, your computation is happening for each parameter, for each layer, and then once the computation is done, your network is waiting. And then you go past that, you are trying to all reduce, and then you are trying to communicate everything. Now your compute is waiting, right? So we are not effectively utilizing the resources. So if you take this optimization, interleaving optimization, what is as soon as you finish your backward propagation for layer 3, L3, you can do the communication for the L3 part of it. So you can interleave that. There is FSDP. There are tons of optimization which gives you different traffic patterns of burst and peak. So you can mix. So it's becoming more and more complicated to design your network. That's exactly what in the keynote they showed, right? They superimposed all the graphs for different types of workloads. They didn't go deep into all the optimizations and the tunings of all those things. Then it is going to be an exponential difference. I'm hoping that UEC will solve some of these challenges which is available today in existing issues, right? So with all those things, I think we talked about it. What makes the AI fabrics unique? It's data intensive. We already talked about it. High injection bandwidth is needed, so they'll try to saturate the network within a few milliseconds. High bisectional bandwidth as well, sustained traffic was we talked about, and low entropy MS. So when you have elephant flows and then you're talking to one GPU sustained, your phi tuple is not going to help you to evenly saturate the network itself. So you need a lossless network. This is imperative because anything you saw in the earlier morning, right, the go back end thing, right? Even if you want to lose one message, Ram was talking about how you're going back end, right? So if you have something and it's order sensitive and drop sensitive, otherwise your training time is going to be exponentially increased. The job completion time is going to be increased based on the network drops and all. So you need to have a lossless network. As we earlier talked about traffic diverse setup patterns and latency sensitive for inference. Let's move on. I think Okay. So Ethernet, we talked about earlier, the message was loud and clear from the morning itself. Ethernet is open, ubiquitous, and then it's already supported. It's a known network for everyone. It's much more easier for you. So Ethernet already supports you all the parameters you want to support an GPU to GPU fabric, which we are talking about today. So it can support 1:1 non-blocking high bandwidth network. For sustained traffic, the key is to aggregate the throughput. So for that, we need multipathing, ECMP, and we need to low entropy. We need to do the multipathing better with enhanced hashing algorithms and now the packet cell spirit technologies and all those things are available to solve that. And then the lastless network, we already support DCQC and Rocky V2, PFC and ECN and all those things. For diverse set of patterns, we have optimized topologies and dynamic buffer tuning capabilities in the Ethernet field, which can be applied here to solve those things. For latency sensitive, we have cut-through switching to reduce your latency of the regular data center switches. So Ethernet already has almost all the capabilities what you need to support your GPU to GPU fabric. So we are trying to more. When they are talked about UEC today, what they are talking about is scaling to hundreds and millions of nodes. But today, Ethernet can already support your GPU to GPU fabric, and that is evident from one of the RAM slides. So all of the 7 cloud providers today support an Ethernet fabric for GPU to GPU traffic. Yeah, Alan.
Hello everyone. Now that we have seen various traffic patterns and the AI fabric requirements, let's see how we can map those requirements into existing sonic features and what are all the features that are required to enable effective AI fabric. The first feature, if you map the AI traffic requirements, the first one is basically we need large radix and high bandwidth platforms. So large radix simply means we need more flow so that you can connect more and more servers, which internally has, like, let's say you have 8 GPUs per server. If you have more ports, you can connect more servers and more GPUs for training, inferencing, and all those fine-tuning operations. And the high bandwidth today, we have a lot of vendors support 400 gig platforms, but few 800 gig platforms. So with that, we should be able to support more and more servers. When it comes to 800 gig, so you can basically connect 64 800 gig, so you can do the math to see how many servers you can connect with that. The next very important feature is Rocky V2. It's not new, it's been there, for PFC and all those things. Now that AI fabric is also in place, and it's latency is not a very problem when it comes to AI fabric, but you can have this Rocky V2 with fine tuning certain parameters. You can achieve those low latency and higher throughput. And then the cut-through switching is basically is more on the AI inferencing, because it's like as soon as you get the destination, you start to forward those traffic, which helps to get the lower latency as well as the higher throughput. This is there in the Sonic API, SAI APIs, and we need some application interface to program this cut-through switching mode. And the next one is the load balancing. It's a 5-tuple ECMP hashing, which is already present, but there are NICs, endpoints that does not randomize the BTH, the Rocky V2 BTH Cupid value to the UDP source ports. So if the endpoint does the UDP source port randomization, we don't need anything at the fabric level. But if that is not done at the endpoint, we may need to introduce additional user-defined fields that are already there in the SAI to include Cupid also as the one of the tuple. So basically, along with the 5 tuples, we will also include Cupid to do the load balancing. The next one is the schedule fabric. Basically, this supports deep buffer and packet spraying capabilities. There is a talk on schedule fabric this evening, so you can get more details about what it's all about and how it's helping for the AI fabric. And the next one is basically so these are all the features available in the community today, and we expect these features to be, is all required to have the effective AI fabrics. The first one is the enhanced hashing. So whatever the hashing is present today is not, it's all static in nature. So you want dynamic hashing. Basically what I'm saying is if you have elephant flow, like Senthil mentioned, if you map two elephant flows to a single port, because it's all static caching, so based on the 5 tuple, you cannot really do justice to the load balancing. We need to really have the finer level hashing algorithms to tune those, dynamically detect whether your port utilization is good, or how many packets are pending in the queue. We need to consider all those criteria before you map to upload to a path or port. And the enhanced load balancing, like I mentioned, we have a dynamic load balancing feature, which is something required to map the flows based on the queue length and port utilization, like I mentioned. And then the adaptive routing feature, it's already, the SAI APIs are already available today. We just need to have the application level code to program those ARS feature. Again, the platform-wise, if you have, as I said, if you have more and more ports, you can connect more and more servers. You can, thereby you can, connect more GPUs, so you can reduce the training time, inferencing time, and all those things you can achieve. And there is a DDDC talk last year OCP. Look at those talks and see how that's helping to get higher radix and all those things, and how we can eventually get better performance for the AI fabric. And the observability is something, we need an open end-to-end congestion controller. Thereby, you can get the congestion information from the fabric nodes and see how we can mitigate those congestions through at the global level. And finally, the Ultra Ethernet Consortium, like Ram mentioned in the keynote. So this is getting momentum now. It's basically, a lot of companies founded this to address some of the challenges we have been facing for many years. And that the focus areas, mainly, how we can use the packet spraying, avoid, like, instead of worrying about load balancing and all those things, how about you spray the packets, through the network, so that you can better manage the, traffic. And then the end-to-end telemetry, these are all the focus areas. You can just go over those EUC website to know more about these solutions. With that, I would like to hand over to Senthil again to cover some of the remaining slides. Thank you.
Thanks, Venkat. Hey, I know that Sonic already covers most of the things, right? I just want to quickly showcase that what can be achieved today with just the 400 gig platforms which are available today and then 800 gig, right? You can double this capacity, right? So if you look at this is supporting 64 GPUs in a single Tomahawk 4 switch, right? 64 ports. You have 8 GPUs per server, and then those servers have close to 10 slots for the NIC 1-to-1 GPU. One GPU maps to one NIC to one 400 gig port, and then you have 2 other separate NICs for doing your storage and your cluster fabric and the management fabric. So this servers boast around 13 PCI slots for you to do all those things, right? So the Ethernet can scale easily. So if you want to 2 to 6 GPU cluster, you can do this with a Tomahawk ports with just 12 switches connected in a leaf and spine cloth fabric today to achieve that, right? This is 32 node. This is a sweet spot for most of the enterprise. We heard about scaling millions, but the enterprises are looking at a smaller fabrics for their training and inferencing piece. So this one gives you a sweet spot for 2 to 6, and you can go to 512 by doubling this capacity, right? And then when you come to Tomahawk 5 and other 800 gig platforms, you can double this capacity. When I say 64 GPUs, you can do 128 GPUs in single switch. In the previous case, you don't have any problems with respect to, we talked about hashing, congestion, all those things are reduced in that. So those things are not there. It's a single switch. You have Rocky and lossless queues. You're good with the 128 GPUs, right? For most of your use cases, for a smaller enterprise use cases as well. You can go to the next slide. Yeah, so in today, if you look at it in a 2-layer, so we could have done it in a pod architecture as well with a 3-stage. So most customers prefer 2 stages to reduce the latency. You can scale up to 2K GPUs today just with the Tomahawk 4 platform for the GPU to GPU fabric. So this can be doubled if you're using a Tomahawk 5. You can double this count just by using this architecture, right? So that's all we wanted to convey today. So the main key takeaways I want you to take today is, so the right network can make or break the performance of the AI fabric. And as you saw, more than network I/O is more than taking 50% of the traffic. 50% of the time is spent in communication in some of the use cases, right? So we need to make sure that, to enable the seamless scaling and the effective utilization of the resources, optimized network fabrics is an imperative today. right? So what we are trying to take away, if you are taking one thing from there, Ethernet is ready for today for deploying your GPU to GPU fabric, AR fabric, and Sonic is already ready to do all those GPU to GPU fabric for you today. And then we at Dell Technologies, we are ready to support you guys. Thank you.
Thank you, Senthil and Venkatesan. For questions, I recommend if you're on the aisle side, come to the mics and ask the questions. But if you can't come towards the mic, I would raise your hand. I can hand off some mic for you guys.
Yeah, like to know the your fabric utilization when running AI workload. What's that utilization look like?
So typically the utilization in this kind of training, as I said, right, depends on what kind of workload you're running. If you're running a large training workload, the fabric utilization is close to 90%, 80 to 90%. Large scale LLMs, like big scale LLMs, right? Yeah. Now those are all busts. It's not all the time, right? If you see, that's what I said. Each traffic patterns is different. It's as I said earlier in the talk, it's going to be idle for some time. It's going to be bursty for some time. It quickly raises to 90%. It comes down, right? So that's a difference.
How does your congestion look like in your network when doing the AI training?
No, the congestion, that's what I'm saying. So for congestion right now, if there is a congestion, so we do have congestion issues. So we need to tune the headroom buffers and all those things appropriately for your workload to make sure that you don't have congestion or lossless fabric. Otherwise, it's going to create enormous pressure on the job completion time for you. So
I think you may have congestion sometimes.
Yeah, we will. That's what I'm saying.
Yeah, okay.
We will. That's what I'm saying. When you have those things, you need to make sure that you tune the fabric for that. Yeah.
It's a good session, Senthil. I just want to know that you explained all the features that Sonic already supports, which helps the AI workload to manage well. Are there any challenges or anything that Sonic does not support, which you see that we should
No,
improve
that's what Venkat explained, right? The feature request. So we do at Dell Technologies, we hope that we'll contribute back some of the features back to Sonic. So whatever the feature requests we talked about, we are working along with a partner to enable those things for you. So Dell Enterprise Sonic already supports those features. Community Sonic today does not.
Oh, so all of them are not supported in Sonic today?
So these are the additional, no. There is one slide before he had all the supported feature. Today, so there is a NIC dependency today, right? So to take a simple case, right, for the elephant flow to hash properly and then to disaggregate your, to saturate your network. So the elephant flows have low entropy. You won't be able to properly distribute your traffic. But if the NIC supports it, NIC can randomize the UDP source port based on the QPID of the Rocky header. If it does that, then you get a higher entropy and your network can saturate it. Then Community Sonic can work for you. If you don't have that, then you need those enhanced hashing capabilities, right, to support those things.
Okay, so those things are not there in the today's Sonic. That's what you are saying.
Yeah, the previous, the enhanced hashing is not there. SAI capability is there.
Okay.
UDF SAI capability is there, but not
Sonic.
the application capability to configure that is not there.
Okay, got it. Thank you.
We'll take 2 more questions before we close because of the lack of time.
Jeff Tensura, NVIDIA. So quick comment, you cannot grow number of QPs to no limit. There's significant implications with regard to performance. Right?
Yeah.
That's why we advise to keep it 4 maybe.
Yes, 4 to 8 is what we typically see. The configuration nickel supports, it supports up to 256, I believe. So I think typically in the customer workloads, what we see is 4 to 8 is what the limit I see in the customer places.
You need to realize there's price to pay.
Yeah.
My request as part of FRR community, you forked FRR a year or so ago. There's many features that are supported in enterprise Sonic that are not kind of upstream back to FRR. We are, with Alibaba people, we are bringing a lot of changes to FRR as we speak. Within 6 months, you won't be able to merge back. Make sure you are on par with community FRR.
Yeah, we heard you loud and clear, Jeff, already. So we will set up some time with you to go review those things.
I have one question about you mentioned the platform, right? Right now, we don't support the DDC, right?
Yeah, that's what DDC is not. So what Venkat mentioning was DDC is available. Previously, there was a proposal for Sonic to support DDC. Some POCs are there, but there is no real use cases. So the DDC is needed is what it says, right? It's a requested feature, right, for scaling. It's not there today.
But do you think in the future, if we support the DDC, it should help to improve?
No, it is there in the future request. I think there's some
yeah, I
confusion.
understand. But what do you think in the future, if we support the DDC, is that also can replace the current topology design and also improve the performance?
Yes. No, it gets you high radix, right? So when you support DDC with the Jericho and Ramon fabric kind of thing, so then you already have the packet spray or cell spray. Yes. So you don't need this QPID kind of thing. So you can at least saturate the network better with those technologies.
Yeah. Thank you.
All right. One last question here. Go for it.
Yes. Yeah, this is Mahmoud from Mao. So I saw that you've mentioned in one slide the enhanced load balancing, and another one that you have the hashing, advanced hashing mechanism that you switch the hashing somehow. And just a question regarding this hashing mechanism, what would be the advantage of using advanced hashing compared to something like packet spraying or something? Like, why would you prefer to use some adaptive hashing compared to
no, so these are, let's assume that these are elephant flows, right? So you have huge number of 1 gig related dense flows coming in, right? So your traffic, you will have, if it's hashes, right, your one of the links is overloaded, right? And then one of the links is not saturated that much, right? So you should figure out right now, based on the tuples and based on entropy, it is going to hash to the same node. And then even though you have one link which is not saturated enough, without this adaptive load balancing kind of technology where you sense how much load is there in the particular traffic. So this is 400 gig link. This is already saturated to, let's say, 380 gig or something like that. And the other link is only 100 gig saturated. But your hashing algorithm is telling you that go and use that link, right? And then you want to make sure that you don't use that link and rather use that 100 gig, right? So right now, the load balancing, it is not taking account how much traffic is going on the particular link. So this adaptive or dynamic load balancing will help you take that flow out and then put it in that link which is not fully saturated. So that way you won't get this congestion. Once you do that, once you have overloaded that particular link, you get into congestion, you get into drops, and then again you get into that cycle of job completion time taking more time. You don't want to get into the congestion state, right? So you want to make sure that your links are fully saturated enough evenly, right? So that's the reason for dynamic load balancing.
Yeah, if I might say also the cell-based load balancing or a bucket-based load balancing would do exactly
you don't have this. No, if you are using a cell-based packet spraying, so you don't have this issue, right? So if you look at it, the future, how it is going right now, again, right, the endpoint-based spraying are coming in. If you look at NIC itself does the spraying part of it, then you don't have the capability. You don't need to have the network fabric active capability, right? So basically the problems are going to the NIC. So you can still use the same fabric without any of those packet cell or spraying feature. Just the NIC spraying, all those things, you will get the same amount of throughput, right? So you don't have to worry about it because the reordering also is happening at the NIC level. So there are multiple different things coming in right now. The NICs are taking care. That's what you would have seen. I think Google announced Falcon Transport today where they do the spraying and reliable connect, right? They do the reordering piece of it. And then if you look at Amazon, they have SRD protocol, which does the same thing. So there are multiple things which are coming in. UEC is also going to propose some of those things along those lines. Right? I think you will see some changes along those lines where we are trying to take away the load from network fabric itself.
All right, thank you. So I'm sure there are a lot of questions here. You can reach out offline to Senthil and Venkatesan for any other questions you have.
Yeah, so we have the same session in the Sonic demo booth tomorrow. If you have, Venkat will be present to answer any questions you have. Thank you.
Thank you, guys.